Appreciate that. Cool, cool. Yeah, and you never know, right? Okay, so and yeah, I mean, I'm always going to live stream at least once, but I think a live stream of your own lecture probably is handier because you just remember where everything is, kind of, right? So oh, and I see. Oh, that's cool. So Jesus H, I appreciate that comment. That's interesting. Okay, good. And like the other day, it was kind of nice because I did one with Jenny and then one without Jenny so that you didn't have to sit through it twice if you were wanting to get right to work. So, all right. Okay, good comments. I really appreciate that. Thoughtful. Thank you. Okay, so what are we going to try and do today? Last time we talked about vector addition. All right. Now we want to talk about vector multiplication. And this gets a little bit tricky. So, there's two types of vector multiplication. There's one type of vector multiplication called dot product and another called the cross product. So we are no longer going to say A times B. That doesn't make sense to people. You have to tell them which kind of times. So you're either going to say A dot B or A cross B, and I'll show you that in just a second. Furthermore, we've got two forms of vectors. We have Cartesian forms and polar forms, right? So you can imagine we might have to learn how to do dot products in Cartesian and polar, cross products in Cartesian and polar. And so there's going to be 4 ways to do multiplication. This is a little bit trickier than 3 times 4 equals 12. So, and there's a lot of silly little details that you have to get right. And at first, it's going to seem very mathy, pretty much meaningless to you because we're not going to be able to do a lot of physical examples because we have to learn the math tools first. Now, that said, oh my gosh, dot products and cross products are pretty useful in physics for learning about real things. For example, if you want to understand torque, you need to understand a cross product. Okay, if you want to understand, say, energy, let's say one that jumps to my mind is like an MRI machine. If you want to know what radio frequencies to use in the MRI machine, you need to know the magnetic energy of the atoms of the nuclei that you're looking at. Well, how do you do that? You use a dot product. And so that's going to be, there are uses for these in other ways too, but those are things that pop out of my mind. When I think of dot products, I think of energy calculations or work calculations in physics. And when I think of cross products, I think of torques and magnetic fields. So those are the ones that most commonly jump out at me. Maybe that's just because that's what I teach, right? So many applications. That said, we're going to start really boring and really easy and work our way up. Why? So that you know the math tools now and aren't learning those at the same time that you have to learn the physics concepts. That's just not fun. That's just too much to be learning at once for most people. So let's take a look here. Let's get that there. Oh, you don't need my email up there. All right, so whoops. Let me get something here. And I think we're on page 60. Okay, so I'm going to give you a quick rundown of the workbook just so you know where things are at. And then if you don't want to listen to me, you can read along and then tune in. Now, what we got through in the first lecture was we pretty much got through all of this page. We got through all of page 60. So this is going to be all about the dot product, all the different ways we can do this, all these different things, including using it to get angles and unit vectors and such. Here's this next page, 61, is an example. I used this one because it's different than one I'm going to do on the board. So you have an extra example to do at home when I'm not around. This problem 3.9, it's basically whatever, A through K. I don't even know how many parts that is, but that's basically each one is like its own little dot product question. So that gives you some ways to practice all that stuff that we were talking about on page 60. So that's our goal to get through. And then with a little practice, hopefully we can get through to cross products at the end. And I was able to get through at least a little bit of this. So our goal for today, September 2nd, is that. September 7th, next Monday, is a holiday. So, and then September 9th, next Wednesday, what we're going to do is finish cross products, talk about, there's the same example, but using a cross product. So notice 60, anyways, we're going to get the coordinate systems too. And that will finish out this chapter. And so by the end of today, you should be able to do pretty much everything in this chapter, except for most of the cross product questions. Okay. And you might even be able to do that as well. Now, I sent you a Canvas announcement or email or whatever the heck you want to call it. So I included all the crap I just said in that email. So after this class is over and you want to get to work, go check that email. And I told you which problems that don't have cross products in them. So you can do basically every problem up to 3.9 and then the little extra ones I said. If you can have all that done by next Wednesday, and come in with questions, the last half of next Wednesday's lecture should be helping you answer questions, get you out of here early if you've already got it. You could maybe do a practice test, and I'll show you where that is too. Yeah, so let's.
So just to
go ahead.
confirm, on the next quiz, there will or will not be dot product and cross product.
Oh, absolutely, absolutely. So basically, the next quiz, every single thing in chapter 3 is in there. So I'm going to get every little detail in there because the goal of this class is to make sure you have this foundation solid. So expect the quiz to be really gnarly, really detail oriented. And there's going to be a lot of questions with tiny little steps, but it's sort of like chapter 1 where there's a lot of details that, man, you really got to pay attention. Esteban, did that answer your question?
Yeah, I was kind of confused because I thought the homework said don't do the dot products and cross products, but maybe I
no. It said don't do the cross products yet. Though because you don't know how yet.
Right. Okay.
So the required. So that's So make sure. So what I did was I told you do all these other problems first. That way, after we finish next Wednesday's lecture on cross products, all you have left are the cross product questions. So if you can get everything except the cross products done by next Wednesday, you're not sitting there over the weekend doing everything. Is that better, Esteban?
Yeah, and so is the next quiz on next Wednesday or
no? It's September 14th, which is not next Monday, but the following week Monday. So we still got a long time.
Yeah. Okay. Now it makes all sense. I was confused a little bit.
Yep. Absolutely. So again, today is Wednesday the 2nd. Next Monday, Wednesday, is September the 7th, no class, holiday, Labor Day. Next Wednesday, the 9th, is finish up this chapter, get all the cross products done so that you could do the cross product homework. And then the following Monday, September 14th, is your quiz at the start of class. And it's going to be, it should be doable if you do the practice and brutal if you don't. Okay. Right on. Okay, cool. Let's see. Any other questions before we get started there? Okay, so let me show you the basic equations, then we'll do some work on the whiteboard. Okay. All right, and so again, we need to first learn this stuff, dot products. And you might have heard me say there's multiple ways to do this. So I want to give you some big picture stuff before we do the whiteboard, okay? This is called a dot product. So A, this is how you say it. You don't say A times B. You say A dot B, okay? Notice the input, I have a vector, something with I's and J's, that's a vector. I have another vector. So the inputs are two vectors. And notice on the output over here, I hope you notice there's no I-hats and J-hats. This is a scalar. By a scalar, I mean something that has a size, a number. It's basically a number without a direction. So we see that the input, we input two vectors. The output is a scalar. Sometimes you may actually hear this referred to as the scalar product because the output is a scalar. Gee, I wonder what the output of the cross product is. Could it be a vector? Well, I don't know. We'll find out. Okay. So there's the scalar product. Now, to distinguish this from the cross product, A cross B looks like the normal multiplies sign. And so this is a cross product. And so it's going to be important what multiplication symbol you use. For cross products, the order in which you do the operation matters. So for scalar products, it doesn't matter if you switch A and B here, you're going to get the same number. But I want you to get some good habits here. Always worry about the order of operations on these things, okay? So make sure you're always thinking about the order. Why? Because when we're doing cross products, it does matter. All right. It'll flip the sign and you'd hate to lose a point just because you did things in the wrong order. That would stink. All right. Okay. So now I do want to point out, like, let's say this number is, we'll do an example in a minute. So let me go on here. This is Cartesian and Cartesian. And so notice this top way of doing it, 3.1, is one way to do it using Cartesian form. This next one down here, it's got magnitudes and direction. And notice this little angle here is explained right here. Theta AB would be the angle between A and B. So this looks pretty good if you have polar form, okay? So this would be great if you know the polar forms of the vectors. This is great if you know Cartesian. Which one looks easier to you? And you can unmute if you want. And Esteban's been talking a lot and I really appreciate it, but let's get somebody else in there. So somebody other than Esteban, speak up. Which one looks easier? It's okay if you're wrong. It's just an opinion. There is no wrong.
Cartesian looks easier to me personally.
Okay. I was hoping someone would say polar looks easier, but that's okay. Like I said, there's no right or wrong.
I was gonna say polar.
So I do think let me put it like this. Do you agree polar has fewer things you got to punch in? How about I say it like that?
Yes.
Yeah.
Yeah. So in that sense, polar looks a little bit easier. However, if you had to pick one of these to know forever that works for every situation in the universe, it's this one. So generally speaking, the Cartesian is good to know because it works in 2D or 3D. This one is great for 2D polar. So if you have 2D vectors, basically in the XY plane, no Z components, man, this one's pretty darn good. In practice, you got to know both. Yeah, and yeah, exactly. Yeah, it's all relative. They're in certain problems, polar is a lot harder. If you know all these numbers, my gosh, Cartesian looks a lot easier than first getting the magnitudes and the angles. That would be a nightmare. So it depends. If I, as an instructor, give you polar form vectors, this one might be good. If I give you Cartesian form, why would you do anything other than that one? So yeah, so they each have their place and you got to know both. And like I said, I'm going to stick you with all of this crap on the quiz. So you got to know everything, people. All right. Now, the dot product of two perpendicular vectors is 0. I can show you this. What if this was 3, 0, 0, and this was 0, 2, 0? Well, what would happen here? Bx is 0. This term goes to 0. Both of these are 0, so that goes to 0. And here, because ay is 0, this one goes to 0. So notice if you have vectors which are perpendicular, like this, again, what I just talked about was one that's like 3 to the right and one that's 4 upwards or whatever I said. If these are perpendicular, they go to 0. So the dot product, in some sense, is a measure of how parallel vectors are. If they're perpendicular, they are not parallel at all. You get 0. If they're parallel, you're going to get a large number. And in physics, we actually add a new word. We say if they're anti-parallel, you're going to get a large number as well. And more on that in just a second. So for us, parallel means pointing the same way, perpendicular, and then anti-parallel means pointing opposite ways. All right. So that's just what we're going to use in physics. Let's go back to that screen. More on that. Now, you could see this as well. AB cosine theta AB. So this is the polar way of doing it. If you have two perpendicular vectors, whoops, sorry. If you have two perpendicular vectors, The angle between them is 90. Well, if you punch it in on your calculator, cosine of 90 degrees is 0. So again, that gives you the same result. All right. Now let's see, where were we here? Let's get back to that. Now check this out though. What if they're anti-parallel? Right? What if the angle between them was 180 degrees? So what if this was 180 degrees? If you punch that number into your calculator, what's cosine of 180?
-1.
-1. Check this out. With dot product, you can get negative answers. Okay, that's one thing you got to know. And so let's go back to our marker example. If two vectors are pointing the same way, you're going to get a large positive number. If two vectors are perpendicular, you're going to get 0. If two vectors are anti-parallel, you're going to get a large negative number. And now if they're kind of anti-parallel, like more anti-parallel than parallel, we should still get a kind of big negative number. If it's close to perpendicular, like this is an angle slightly bigger than 90. You'd probably expect an angle that's maybe small and negative, close to 0, because it's not quite perpendicular. So it's close to 0, but not quite. And negative because it's a little more anti-parallel. Whereas this one would be kind of a small positive number. It's close to 90 degrees, so it's close to 0, but it's more parallel than anti-parallel. And likewise, okay, and I'll do a simulation here in a minute to show you that. Oh, what the heck? Let's have some fun. Let's do it now. So to give you a feeling for this, oh, this is a bunch of words. Forget that. Okay. And so the idea here is, let me do this really quick. Let me get rid of that cross product. So I'm going to run this program again. And so the idea here is this. Oh, geez. Oh, I commented out one of the things I need. Sorry about that. So I sent, oh my gosh. All right. I forgot. Okay. I got to comment out these two lines too. Sorry about that. Oh my gosh. So I had both the dot products and cross products in there, and I want to just talk about the dot product right now. Here are two vectors, and I sent you this simulation so you can learn how to play with this yourself. But the idea is, look at these two vectors. I hope you agree these two vectors look anti-parallel. And by the way, these are Minnesota Vikings colors, not Los Angeles Lakers. After they got rid of Kurt Rambis, hey man, they lost it for me. If you guys don't even know Kurt Rambis, good for you. If you don't care about sports, I'm fine with that too. I'm just making a joke. All right. So look at these vectors here. Now, this looks a little bit funny. The vector A is my purple arrow. Now, you may not have seen this notation before, but this means 3 in the I hat, -3 in the J hat, 0 in the K hat. So basically, it's a 2D vector. The vector B, which is the yellow arrow, it goes -2 in the I hat and 4 upwards. So if we could try and draw this crap, right, this is the purple arrow. So that is, what is that? 3 in the I hat. That's this one. And then we have -3. So there's 3 downwards, right? And you can see it looks like a 45 degree. And I'm not going to write the -3 because I already did write the negative with that arrowhead. That arrowhead says the negative. Okay. Now over here, what do we have? 2 to the left. So that's 2. That's this number right here. 2 to the left. That's the arrowhead for the negative. And then we've got 4 upwards, right? So that's 4 upwards. That's that vector. Now, right here, you could see the angle between these vectors. I actually had the computer printed out for me. This is the angle between them. All right. So that means this angle right here is something like 160. Let's just say it's about 162. Okay. And I hope you agree that is very close to 180 degrees. Right? These vectors are very close to anti-parallel. They're not perfectly anti-parallel. They're close to it. So now what's going to happen here? Okay. Here is the magnitude. Whoops, sorry. These are the magnitudes of the two vectors. Ignore all the sig figs. That's just, who cares? All right, that's just the code. But we see that they're both about 4.5. There's the magnitude of these two vectors. And now look at this. I had the computer compute the dot product, and I'm going to show you how to do all the steps in just a minute. But the dot product is negative 18. Now, if we're trying to check this answer, that's where we need to know the physics, the physical meaning of these things. So think about it. The biggest a dot product can be is you just take the two magnitudes and multiply them together. So if they were perfectly parallel, you'd get about 19. So that means the largest possible dot product you could get with these two vectors would be 19 if they were both pointed the same way. So if you had a vector of magnitude 4.24 and another one of magnitude 4.47, the largest possible dot product would be 19. Notice we have a large negative number. It's large because it's close to this value, and it's negative because they're close to anti-parallel. I'm going to pause there and see if this is making any sense at all. Is that helping at all for kind of a visual? I have no idea if that's working.
So it's just the multiplication of the magnitudes gives you that. Then the angles are added, or I forget, because I remember in electronic class when you added.
Oh, that's different. Circuits are different.
Phases. Okay.
So if you're talking about phasors, that's a little bit different. That's physics 163. So that's like about a year and a half from now for us. So that's very different. That's using exponential functions, complex number values, and I don't want to go into that right now. But no, it's not like that at all. That's something different. It relates to it. It's more basic than that, what we're doing. So yeah, again, all we're doing now is trying to get a feel for these vectors. I'm going to show you all the back end, how to do the math to get these numbers right now, okay? So now we're going to start working on these numbers. But before I do that, let me do this. I'm going to go into this code, and I'm going to change this to make them both positive, like this. Now, look at, these are my two vectors. This is the x coordinate, y coordinate, x coordinate, y coordinate. Think what the vectors are going to look like when I run the code. Hopefully you're thinking they're both in the first quadrant because everything's positive. And now think to yourself, are they going to be close to parallel or close to anti-parallel? Let's see.
They should be close to parallel.
Exactly. Those vectors look very close to parallel, right? They're almost pointed the same way. Now look down here at these numbers a little bit. And what we see here is, sorry, let me get this bigger. The idea is these two vectors, they still have the same magnitude, but they're pointing a little bit different direction. Now notice the dot product is positive because they're close to parallel. And now watch this one. What if I do 3 comma, let's do 3 comma 4. How about 3 comma negative 4 and negative 4 comma 3? Think which quadrants they'll be in. Again, this is X, this is Y, this is X, this is Y. Think,
2 and 4.
Let's take a look. And now think, are they going to be close to parallel or close to perpendicular or close to anti-parallel?
Anti-parallel.
Close to perpendicular, I think, aren't they? Oh, whoops. I had my numbers wrong. Did I flip it? You were right. They were, okay, so you were right. They were close to anti-parallel. I must have flipped something in my mind when I was typing them in. Nice job. Okay, so this is why the computer is nice, because it helps us catch that. So in this case, we see here we go. Oh, whoops, I flipped them both. That's why. If you flip just one of them, if I flipped the minus signs on just one of them, they would have been perpendicular. We'll do that in a second. So again, we see here's the maximum possible size. This is a large number. It's negative because anti-parallel. And let me do this. Let me flip one of these signs here. Sorry about that. Wasn't paying attention. This time, hopefully they're close to perpendicular. And notice that's a right angle right there, right? And so when you see that, when we scroll down, the dot product had better be 0, and it is. So here, the largest, they each have magnitude 5. The largest it could be is 25. We get 0 because they're perpendicular, and the angle between them is 90 degrees. All right, let's get to doing the math on paper, because at first, it's pretty hard to understand all this if you don't first understand it on paper. All right, so let's go ahead and do that. All right, before I do that, any questions? All right. And remember, you can add it to the chat, and Memo might have had to step out for just a second, but he'll be back any second. So Yep. We just got to work through the math now, right? Okay. So that's to give you, yeah, I sent that to you in an email, Adrian. And I also sent you instructions for how you could do it yourself. So starting from scratch, if you've never coded in your life, and if you want to, we could talk about it in office hours as well. And I think if I walk you through the code in office hours, you'll gain a new appreciation for why you need to learn this stuff and why it's important to know how all these different things work. So yeah, for sure. It's in the email I sent you. Yeah. All right. All right. So let me get into here. Yeah, and Python is it's pretty sweet. If you don't know what Python is the computer language I was using to make those in. I literally made that in office hours with a student watching me in like 2 minutes. So it's, imagine how powerful that is for doing your homework and stuff. And you know, as a professional, you're not going to be doing everything by paper and pencil. That said, you still need to know how to do it paper and pencil to get a feel for it. And that's what I was just trying to do with that introduction, was give you a feel for it. Why? So we have some intuition for checking our answers. All of this work that we're doing right now, as a professional, you're always going to use a computer, right? But if you don't have intuition, basically, this is as simple a way to put it as I can. If you don't have intuition about these things, how are you going to check if you remember to use the degrees or radians button? Or when you're typing in a code, is it using degrees? Things like that. And you really need to have a feeling for these numbers and how they should be outputted. And that's what the paper and pencil work will do for you. It helps you check yourself for mistakes before you send the Mars rover out there and forget that you're in centimeters there and inches, and the whole thing crashes and you lose $100 million. Okay. All right. So whatever. If you don't know what I'm talking about, that's a true story. I'll tell you later if you want. Some people used the wrong units, didn't keep track of their units, crash, $100 million. Yeah, not very good. Made it all the way to the planet too, and then crashed. All right, so we could look that up later. All right, so now what am I going to do? I'm going to try and use these methods to analyze some vectors. If you don't want to listen to me, you could look at this page right here. This page, I did a different example. So if you think, you know what, I've seen vectors in my math class, good for you. Do this example and start doing homework problems instead of listening to me. If you are clueless, let's do this together and let's start from scratch. So again, this is an example you can use afterwards. I'm going to do a different example. All right, so let's use a vector. How about we do, you know what? I'm going to raise this up a little bit. Sorry. I want to have some room to work. And let's just do something up here like this to keep things easy. Let's say this is vector A. And let's say the size of it, and I'm not going to do sig figs on these ones. The ones in the workbook, I do it. So I'm not going to do it up here because I'm going to run out of space. So apologies for not being able to do everything. So let's say this is 5 newtons. So maybe that's a force applied to something, 5 newtons. And this angle to me looks like it's about 30 degrees. Again, who cares about sig figs? Now let's say there's another vector. And let's say this is 7 meters. For some reason, it has different units, whatever, it doesn't matter. This is vector B. So these are 2 vectors. They have different units. It doesn't matter. Oops. Now, and in this case, I'm going to actually write it. This angle looks a little bit easier for me to work with, so I'm going to use this. This to me looks like, ooh. Let's say, just to keep this easy, let's say this is 40 degrees, okay? Already I can see these vectors are not perfect. I didn't draw them perfectly, but they look a little bit like they're close to perpendicular, but not exactly, right? And in fact, I want to change this number to 20 just to make it a little bit easier, okay? So let's say that's 20. So now they're not exactly perpendicular, and that looks maybe a little better to me. All right. In this case, I'm going to move this over to here, just so I can see it. This is 5 newtons long. And I'm going to look at this one, and this is screaming out for me to do one of the different dot products. I want to do A dot B, right? So I'm going to hold this up here. If I'm going to do A dot B, think to yourself, which one looks easier for this part? Should I do the top line or the second line? I hope you think the second line. Why? Because we already have angles on the board and we already know the magnitudes A and B. So I'm looking right here at this, and I notice I know A, I know B already, and I bet I can get this angle just by looking at the whiteboard. So in this case, polar is way easier, right? So when I look at this, if this is 20 degrees, I think this is 70 degrees. I just like having all my angles labeled. And this one down here should be 50 degrees if I need it. Right? So 50 plus 40 is 90, 20 plus 70. All right, got it. So now I'm going to write this out. Ooh, we're going to party. I'm taking the caps off. Cap-free living, people. All right, so what I want to do is A vector dot B vector, and I want that to equal something. And I know, what do I need to do? I need the magnitude of A, and we're going to try and get in a good habit of always putting the first vector first. Why? It doesn't matter for dot products, but it does matter for cross products. So B, start good habits. Now this is B, and remember, this is A, the vector. This is A, the magnitude. Part of this chapter is whipping you into shape, so you always pay very close attention to whether there's an arrow, a hat symbol, or no arrow or no hat symbol. More on the hat symbol soon. Now, I need an angle here. Is it 20, 50, 40, or 70? What angle should I shove in there? And again, I'll hold this up. Think, let's read the definition. You don't just grab any old angle. I need the angle between A and B. So let's look. What is that?
It'd be 70 plus 40, right?
Exactly. And so that's one of the things you got to watch out for in a physics class. Sometimes we'll give you one or two of the angles, but we won't give you the angle you need, and you got to do a little bit of scratch work first. So good job. I was trying to trick you. You didn't get tricked. Awesome. Now remember here, A is, what is this? Okay, that's right there is A. B, that's right there. So go ahead and punch it in, see what you get. And then we'll go ahead and redo it in Cartesian form, okay? So A is, let's see, 5. B is 7. Cosine 110. I'm going to reach for the calculator for that. Actually, I'll just write it as cosine 110.
So because those are scalar, then we don't have to worry about the unit?
Ah, you caught me. So I was trying to trick you into thinking this was correct. This is absolutely wrong. Do you agree? Who was that?
Jacob.
Jacob, what did I do wrong?
Well, newtons are totally something different than meters, so.
Oh, that's not a problem. Yeah.
Oh.
Yeah, it turns out this is totally fine. But what you were right. He started thinking about units, which is what I wanted you to. I was deliberately trying to trick you. Good. So in this case, you have to include the units when you do the math. Nice job. Excellent. And now it turns out a Newton times a meter is actually one type of unit called energy. So this could be a force. This could be the distance a box gets moved, and this will be the total amount of work done on the box. In cross product land, this could be the force, and this could be the lever arm, and this would be the total amount of torque. So it turns out Newton meters are very common units for dot products and cross products. And we just call them Newton meters. Nice job. Outstanding. Well, did I address your question?
Yeah, perfect. Thanks.
Right on. Yeah. So I was deliberately trying to trap you. You caught the trap. So now let's punch it in. So 5 times 7 times cosine 110. I got negative 11.9. How about we just say it's about a negative 12, right? Now the units, they're Newton times meters. You could switch the order of the units, but I point out that's probably a bad idea, because if you have this M before that, people might think you mean millinewtons. That's not good. So this is newtons times a meter, okay? All right. So we know that's the output. I'm going to write that down up here for reference. Okay. Hopefully you got that. Now let's think. What's the biggest these two vectors? It could be 35, right? 5 times 7. The biggest you could get with these two vectors would be 35. This is not close to that. That means these are pretty close to perpendicular. And we see that 110 degrees is close to 90 degrees. So we should expect a small number compared to the multiply the two magnitudes. Good. Furthermore, does this minus sign make sense? Yeah, they're more anti-parallel than parallel, right? So if I just put this up here and bring it up to the screen, that's closer to this than it is to this, right? They're pretty anti-parallel there. So if they're closer to anti-parallel, we expect a minus sign. And then because they're close to perpendicular, we expect it close to 0, not close to 35 in this case. So far, so good? I'll just pause. I see there's some chat. Let me check. Oh, yeah. Okay. All right. Sounds good. And now what I want to do is, even though we're done with this problem, let's do it again using the Cartesian form. So the first step is get your vectors in Cartesian form. So I'm going to put the screen up. Whoops. Oh, not that. Okay. So race me. I'm going to try and get A as a Cartesian form and B as a Cartesian form. And I better put the cap on the black marker now. It's going to be something in the I hat, something in the J hat, and it's going to be in newtons. Likewise, B is going to equal something in the I hat, something in the J hat, and that one has units of meters. We're ignoring sig figs for this problem, all right? Now, in this case, you could go ahead without me. I don't have room to do everything here, but this is opposite the 20. So this is going to be a 5 sine 20. Sorry, I didn't write the units. That's a 5 sine 20. This one's adjacent to there, so I'm going to write this as 5 cosine 20. Now here, this is getting messy, so I'm going to erase this one. I know that this side here is adjacent to the 40, so this one is adjacent to the 40, so that's going to be 7 cosine of 40. You could have also said that's 7 sine of 50. That's the same. This side is opposite that, so that's 7 sine of 40. All right, and so the idea here is, in practice, I know it's always going to be the magnitude times either sine or cosine, right? When I get the components, it's always magnitude times cosine or magnitude times sine. One of those two things. How do I figure out which it is? I look at the angle. If I'm adjacent to the angle, I write cosine. If I'm opposite the angle, I write sine. And then here, I'm adjacent to 40. That's why the y component got a cosine for some reason here. And up here, it's sine for the x component. And then remember, I still have to remember the plus minus sign. So this one right here is the spot you might screw up because it's negative. Race me. Go. See if you can beat me. You probably can. So 7 sine 40, 7 cosine 40. And just keep 3 sig figs is plenty. A is cosine gets the x in this case, so that's I'm going to say about 4.70. Normally we would keep 4 sig figs, but I just don't have room, okay? This one's, they're both positive. Yeah, good enough. Usually you keep an extra digit if the first digit is a 1. So by doing this, because I only kept 3 sig figs, my final answer should only be correct to 2. All right, whatever. I did remember the units this time. Always check. So now we could do so now what do I need to do? Remember, it's going to be AX, BX plus AY, BY, and we don't have any Z components, so I'm not going to write them. But if there were Z components, you'd have plus AZ, BZ. Easy, AZ, BZ, cover girl? Well, that doesn't quite work. All right. So in this case, AX is 4.7. I guess that's why physicists don't become marketing agents. Worst slogans ever. BX is, ooh, negative 4.5. Ooh, spicy. My life is so crazy right now. Oh my gosh, I'm excited. Okay, now this one, AY is 1.71. We'll keep that digit laying around. BY, 536. Now, humor me. What did I forget? Somebody that hasn't spoken up, somebody different.
With the I and J hat?
Nope. Remember this, and that's a good thought. And that was one of the things I was going to ask you about actually right after this. So you caught it first. Notice carefully. These ones are vectors, right? They have I's and J's. The output is a scalar. There's no I hat and J hat in the end. So that was a good thought, but that's not true. That will be true for cross products. So on the cross product, we would need the I hats and J hats. For the dot product, we don't. What else? Somebody else. Good guess.
Units.
Units. So think, this is going to be a Newton meter. This is also going to be a Newton meter. So I don't have room to write it. We'll do it on the final answer. Go ahead and punch it in your calculator and see what you get. Hopefully it's 12, right? Or was it negative 12? It was negative 12. So 4.7 times negative 4.5 plus 1.71 times 5.36. I got negative 11.98 this time. Last time I got negative 11.97. We see that when we round too early, we're off in the sig figs. So this one was negative, basically negative 12. When I round to 3 digits. So we got lucky. Obviously, the more vectors and the more operations you do, the more screwed up this number is, and the less likely you could trust that third sig fig. And so this, you can see we get the same result, whether we do it with polar or whether we do it here with Cartesian. Again, what are some things to notice? You guys caught all the big ones. Plus minus sign, think about it. Size of it, is it close to the 2 magnitudes? Is it close to, in this case, 35 because I had a 5 and a 7? No. Why? It's far from, it's close to perpendicular. This should be a small number. It's closer to anti-parallel than parallel. It should be negative. Don't forget the units. Make sure you don't write the I hats and J hats on a dot product. And that's kind of all the key elements that we're supposed to learn there. What do you think? Does this make some sense? Just give me some feedback. You could do the thumbs up or thumbs down. Or
Seems good.
yeah. Did they give you an option for thumbs down? No, they don't. I love that. That's pretty cool. So I'm always going to be a good teacher because you can only give me thumbs up. Sweet. Easy. I never knew online teaching could be so easy.
Are you sure? Because I think I'm thumbs downing you right now.
I hate this too. This is the worst ever. All right. So, because normally what do I do in class? I walk around and check your work and say, oh, you forgot a minus sign, and check, you know, all this stuff. So it's much easier to check in person. Believe me, we all hate this. Okay. That's, let's get back on task here. So, all right. And remember, you've got extra examples with better sig figs in the workbook. So let's do that. Okay. All right. Appreciate the feedback. All right. Oh, whoa. No, not that. This. What is this? Let's close that. Okay. So what have we done? We've done these two things, and that's the goal of it here. And we understood this. Now, here's something that you need to know. We haven't done this yet, but we're going to do it maybe in a minute. The magnitude of a vector in three-dimensional space is a little bit different. Normally, we do x squared plus y squared. If you have a z component, just add in the z squared. Don't overthink it. Okay. These are some tricks I want you to memorize, and I'll explain why as the math goes on. You just have to trust me here, okay? But I want you to know this fact. I hat dot I hat equals 1. Why is that?
Is that because of 180 degrees?
Yeah, you're on the right track. So sorry, you're absolutely right. Let's think about the angles and draw a picture. So notice immediately, I think that was Esteban, right?
Yeah.
Yeah, so he's thinking about it in terms of what it looks like, and that's what I have to do. And for some reason, I can't think without drawing. So that helps me understand things to draw it. So having a little scratch paper to write, try to do it all in your head, not a good idea. Well, let's think. Let's say this is I hat. Okay. Well, let's make another copy of that. Isn't this also I hat? And what does I hat mean? It means to the right. I'm going to go even farther and say it means 1 unit. It is a unit vector. So a hat means a unit vector. It's a special type of vector. It's still a vector, but it's a unit vector. That means it's 1 unit long. So that's what I hat means. It doesn't just mean to the right. It means 1 unit to the right. So if I wanted to get the size of I hat, the size of I hat is 1. That's what it means to be a unit vector. Okay, this means the size of the unit vector I hat is 1. All right, now just showing you with these markers here, what's the angle between those two markers right now?
0.
0, right? So, and I really do appreciate you guys speaking up. I know it's hard because Zoom is just hell. So it really means a lot to me that you guys are willing to unmute and do that and participate. It just kind of gives me some feedback. So I do appreciate it, even though it's not fun for you. Yeah. So drawing that again, I just erased it. I don't know why. There's another copy of I hat. And you just told me the angle between them okay, angle is 0 degrees. So let's do this slowly. I hat dot I hat, I'm going to use the polar form, okay? The polar form means the magnitude of the first one, that's 1. The magnitude of the second one, that's also 1, times the cosine of the angle between. Well, what's cosine of 0 when you punch it in your calculator?
1.
1. So what's 1 times 1 times 1? That's just 1. So we see that I dot I is 1. Well, if I did this another way, what if I did I dot J? And I should be careful. I should say I hat dot J hat, not I dot J. I'm a bad
0.
person. Exactly. What's the angle between?
90.
90 degrees. And what's cosine of 90 degrees? 0. So this, now you could go through this every single time, or you could do what I'm asking and memorize. Give me a sec. Oh my gosh, come on, computer. Memorize this crap. Look at it. Doesn't that make sense? Anytime the vectors are parallel, you get 1. Anytime the vectors, now I should be careful. Anytime the unit vectors are parallel and you dot them, you get 1. Anytime the unit vectors are perpendicular and you dot them, you get 0. That's another way of saying it's a measure of how perpendicular two vectors are. So if you want, you could imagine foiling this out. And when you foil it out, you could use these things, and that would help you learn this fact. So that's, yeah, this first line up here, you could think of it as being a corollary of this, or you could think of the 3.5 as being a corollary of that. And let me see, I want to check something down here. You could see I kind of did an example right here for three-dimensional vectors. And what I did is I just plugged in all that stuff, and there you go. So if you need an example of that, I guess, yeah, well, that's cool. All right, next. How to turn any vector into a unit vector. All right, now let me show you why you care about this. You might think this is dumb, but it turns out it's hugely useful in three-dimensional space. It's really easy when you have a 2D vector like this. Let me just draw a random vector here. If I give you a vector, it's really easy to say, oh, well, here's the size, 7 meters, let's say, and here's the angle. This looks about 140 degrees, let's say. It's really easy to give you a magnitude and a direction. If you have a three-dimensional vector, it doesn't work so easy, right? So, for example, oh, whoops. Let's go over here to this one, all right? Let me comment out all this stuff here. And what I could do is I could make a new arrow. Oh, actually, I have it down here, right down here. So in this case, I could run this program. And now this is the idea. The big purple arrow is the vector, right? And then the little white arrow hidden inside of it there. Whoops, come on now. This little white arrow hidden inside of it is the unit vector. Now, in 2 dimensions, you might be saying this is stupid. And okay, yeah, whatever you think, that's fine. Let's go and do a 3-dimensional vector and see why this gets tricky. So let's just add in a 7 here, or how about a 2? Okay. Give it a second. So now the idea is if you look at this vector in 3-dimensional space, it's not exactly lined up on any of the axes. How do you specify that way, right? You often people say, oh, which way do I go? Which way do I go to get to the park? Oh, it's that away, right? How do you say that away in 3D? By using a unit vector. A shocking thing, no, it's not shocking, but let's pretend it is. A shocking thing about unit vectors. They have no units. It's like, it's the misnomer of the century, but that's fine. Let's learn why unit vectors have no units by looking at the definition. So again, why are we learning this? Because in 3-dimensional space, that's how you specify a direction. You can't, it's not easy to do it in polar form. You'd have to use an azimuthal angle and the other angle too. So whatever, let's get into this. So let's go back to here. It's really easy. Take a vector and divide by its magnitude. And I want to zoom in on this to show you something that I want you to pay attention to. Oops. Okay. This is what I'm looking at right now. Just give me a second. I'm looking at this. You are expected to know this stuff really well. This is a vector. This is a hat vector, a special type of vector with length 1. This is the magnitude with no direction at all. You have to know the difference between A, and A. A and A and A are all totally different, but we sure sound like we're saying the same thing, eh? Don't you know? All right, so we're going to talk about the differences between a hat, a vector, and a magnitude right now on the whiteboard, okay? And let's do an example, but basically you take the vector and divide by its magnitude. So let's take a look at this one and go up to the board. All right. All right, and so let's say we get, oops, I got my calculator on the cable there. I'm going to do a fun vector. Let's say, ooh, let's have some fun. Oh, that looks like too much like the 4. Let's not. Let's just say, let's say we have a vector n for some reason. I don't know. I haven't used letter n today. So n is a vector. Maybe it's a normal force vector or something, all right? And let's say it's -3 in the I hat plus 4 in the J hat minus 12 in the K hat. Okay. And maybe it's a force. I don't know. Let's just say it has units of meters. We haven't used meters per second today, right? Let's use meters per second for this one. All right. So let's say we have some weird, maybe it's the speed of a nomad. And I should be careful. This would be the velocity of a nomad because it's got the speed and direction here. So let's figure out n hat. N hat is different than n vector. So this is called n hat. It's a little chevron instead of an arrow. So this is an arrow. This is a hat. That's equal to n vector divided by n magnitude. So n equals n over n. What? Okay. I already know what n vector is. Can anybody tell what this magnitude is right off the top of their head? It's all right. This is a 3, 4, 5 triangle. Then I have a 5, 12, 13 triangle. So the magnitude is actually 13. Anyways, that's a fun one that's why physicists like this 3, 4, 12. Okay, so I'm going to first work this out. I'll shut up now. I'm having too much fun today. I did have a diet soda, which makes me crazy. Oh my gosh, I'm losing it, people. Sorry you got to put up with this. You never know what's going to happen on Zoom.
I like it better when you get crazy.
Yeah, it's like maybe there's a reason to stay awake slightly. Like, what stupid thing is he going to say next and get himself into trouble? All right, so I appreciate that. Yeah, is anything we can do to make this slightly less boring, right? Anything. It's a lot more fun in class when we can, talk to each other. All right, so this is the magnitude. And so I'm going to just work this out. Just give me a second. I'm going to punch this in on my calculator really quick. What is it? Oh, I know it's 13.
You already said 13.
You're right. So, all right. So is everybody cool with that? If you want, you could check it on your calculator. Why am I staring at you right now? Why is it not right?
Units.
Units. I'm going to harass you all the time until you guys are harassing me about it. Okay. So again, I gave you the units here. I started doing the math, and then you always got to check when you get to your final result, just double check. What were the units? Now think about this. If you put meters per second on each of these, you get a meter squared per second squared on each of these. Sorry, I got to write so small. Right? So you'd end up with that. And then when you take the square root, you get apples plus apples plus apples. Actually, apples squared plus apples squared plus apples squared equals apple squared. Then you take the square root, you get back to apples. All right. All right.
Or applesauce.
That's right. That's right. We'll put some sauce on that. That's probably some kind of phrase, I guess. But oh, I need a little bit lower too. There we go. Okay. Now let's get this n hat. N hat is equal to this vector divided by this. What's going to cancel out? What does every single term have in it? Go ahead.
13.
What's that?
13.
Nope.
Or meters per second.
Yes. Look, meters per second, meters per second, meters per second, meters per second. That should drop out, right? Let's do it. So I should get, and again, we're being lazy with sig figs because of whiteboard Zoom hell. Okay. And I could see the units drop out. Unit vectors have no units. No matter what units the vector has, the units drop out. It's sort of like when you talk about angles in calculus, usually you use radians. Radians have no units. So an angle basically has no units. We don't think in degrees when we're doing math. So when you talk about a degree heading, really that's like radians, which has no units. So all these directions that we've been doing in polar form, they don't have units. This doesn't have units either. And that's a good thing, right? We want to specify directions the same way. Angles have no units in radians, and neither do hat vectors. So now I'm just going to punch that in, and I'll let you punch it in, okay? And I'll bring it up in the code while you're punching it in, so we can visualize this instead of just having stupid numbers on a whiteboard, okay? And I see there's a chat question. Yes, Jacob, yes. That's it. Diet soda. Okay, so what do we have? -3. 4, 12. I'm going to run this one. All right. So here's my vector. Whoa, look at that thing. Oh, where's the Z? Oh, there it is. So notice there's that vector, and it's kind of hard to see, but it doesn't line up perfectly on the axis. Right now, I'm staring right at the axis. I could see it right. Here's the axis, right? I'll line it up so I'm looking straight at it almost. Whoops, come on. Oh my gosh, what did I do? I have no idea what happened to my computer really quick here. What? I think I took an image somehow. Whatever. All right, that was weird. I don't know what I just did, but yeah. I'm just trying to show you that I'm not exactly there. I'm lined up on the axis. This vector is kind of off axis, and that's because all the components are not there. Now look down here. We do see the unit vector is kind of pointing off a little bit to the side as well. And here's all the parameters underneath, just to give you an idea. Here was the original purple vector. Here's the magnitude. Oh, whoops. Yeah, whatever. Then this is the magnitude of, oh, wait. Oh, I did it twice. Whatever. Who cares? Here's the hat vector. And hopefully those are the numbers you got. If you want, you can do a quick screenshot or just do the homework later, right? That's more important. I'm going to pause. Okay. Questions on that one? People doing all right?
Yeah, you can't do that with polar form, huh?
You could, but you have to give, it's sort of like on the planet Earth, right? You have to give a latitude and a longitude. Those are two angles and a radius. So if you're trying to describe a location with polar coordinates, you got to give two angles and the radius. Azimuthal and, geez, I'm forgetting the other one right now. You guys could tell me in the chat. It's not going to come to me because now I'm under pressure, right? So yeah. All right. So you can do it, but it's tricky. Are there times you would want to do it? Absolutely. What's the big example? Telling people where you are on the planet Earth. Why would you use angles there? Because it's easier on the planet Earth, which is a sphere. Everybody's got the same radius. So then if you're telling where somebody is on the planet Earth, you only need two coordinates instead of trying to do X, Y, and Z. So yeah, there's a time and a place for all these. There's weird coordinate systems too. Let's leave it at that. Esteban, did that answer your question?
Yeah, and so the unit vector only points the direction. It gives no magnitude or anything, right?
Right. It's always got size 1.
Right.
Chewbacca hat is a unit vector. There's some vector Chewbacca. I know the size of it is 1. I don't know which way it points, but I know the size of it. Taco hat, size 1. Yeah. Okay. All right. Let's see what's next. Angle between two vectors. Okay, so let's go to work here with the all right, sorry, just a second. Now, I could tell I'm slightly slower than my last lecture, and that's my fault. I don't know why. But yeah, I want to talk about this angle and try to get to cross product as quickly as possible. So if I go a little bit too fast for you on this one, just be aware, my earlier live stream, I did this a little bit slower. So if you need to see this in a slower way, maybe go check out the live stream from the earlier one on my YouTube later. That said, let's get to work. What am I going to do here? I'm going to try to figure out the angle between two vectors. Why am I going to do that? I'll show you. Let me give you an example in the real world. Where is that? Imagine you're trying to build something like a civil engineer like this. Maybe you want to build some structure. There might be a need for figuring out the angle between these two cables. Maybe you want the angle to be something and design it a certain way. So you need to do some math that gives you the output angle. And maybe you want all the cables to be pulling at right angles because that's a good design. You would have to do some math to figure out some dot products so that you could figure out if these angles are right or not. That's why we're doing this, okay? In real life, there's a reason you might care about this stuff. Right now, we're just doing the math. Come on, where are we? Oh my gosh, where is it? Okay, we're doing this. So I'm going to figure out the angle between two known vectors. Now look at it. What do you do? Basically, I know this is the definition of the dot product, right? The dot product is equal to itself. Let me get my regular annotation here. All right, this seems intuitively obvious. A thing is equal to itself. This is one way to write that thing. This is the other way to write that thing. And now I just solve for theta and get this thing. And so you can memorize this if you want, or you could just do this. I remember it this way, I guess. This is what I remember. So that makes it easy for me. And if you're into hat vectors, it turns out there's this clever trick that actually works out like that. So let's do a quick angle between and see what turns out, okay? All right, here we go. So let's do the board. Okay, let's say we've got one vector here. Let's say this is 20 degrees, and let's say this is 7 meters. And then let's say we go up here. Let's say this is, actually, you know what? You guys are already pretty good at going from polar to Cartesian. So let's cheat and give you the Cartesian forms, because I keep giving you the polar forms. I gotta speed this up some way. This will be the way to do it. I think I'm confident. Let's say I gave you a vector here that A was equal to 3 in the I hat minus 4 in the J hat. And let's say that's in meters, okay? You could get that from a picture probably. And let's say vector B is equal to, how about 2 in the I hat minus 15 in the J hat, and let's say that's newtons, okay? And so now what am I going to try and do? I'm going to try and get the angle between. So I'm using this crap, okay? And you could follow through the steps later, but I'm just going to go right to the result so you can see how this works out. Okay, I need the magnitude. So the magnitude of A is equal to the square root of 3 squared plus 4 squared. That's equal to 5. Whoops. And then I check the units. That's meters. The magnitude of B is, I got to get my calculator for this one. That's the square root of 2 squared plus 15 squared. Wait, shouldn't I use the negative? No, it doesn't matter because it's squared, so I'm lazy. Okay, so 2 squared, that's 4. Whoops, that's square root of 229, right? Oh, come on, calculator. Give me math print mode. So you might encounter this too. A lot of students see this. Like, that's about worthless to an engineer, right? What does the square root of 229 even mean? So what you could do is you can hit the mode button. Maybe. Did I not hit it? Whoops. Mode button there. And then if you scroll down, classic. And then now I can get out of there by hitting second quit. And now I can do square root of 229. Freaking calculator. 15.13. Newtons. All right, so now how do I get this one? It's going to be AX, AY, BX, BY, And then there's going to be a B. There's going to be an A. I got all the pieces. I think I could do this, right? And don't forget, AX is going to be 3. I'm going to zoom in for this one. Oh, I can't. I need to use this. So AX is 3. AY is -4. BX is 2. BY is -15. And then A and B are the magnitude of A. This is the magnitude of it. That's 5. Whereas this one was, I think it was 15.13. And then let's be careful. Do I need units on this? Let's think. A was in meters. This is in newtons. So I get meters and newtons, meters and newtons. But on the bottom, I also have meters and newtons. All the units will actually drop out in this particular case. So you should include units. I'm in a hurry to get this problem done, but I will tell you, if you included the units, you should find they all drop out. Okay. Oops. All right. So now I'm going to punch all this in because it's a number. So that's 6 plus, oh, that's 66, right? 6 plus 60, because the minus signs cancel. So 66 divided by 5 divided by 15.13. So if you get lazy and you don't want to do parens on the bottom, right, you do 66 divided by 5 and then divide it again by the second number, and the computer does order of operations. I got 0.872. All right. And now I'm going to cosine inverse this side. Now I only wrote 0.872, but if I'm careful in my calculator, right, I just hit cosine inverse, and then I'll type in answer. So second answer, 29.2. Okay. So what did I say? 29.3-ish. Almost all fits there. Whew, that was tight fit. Okay, so this is how you could get the angle between two vectors. All right. Now, what did I want to say about that? Oh, it's usually good to draw a picture to make sure this makes sense. I never trust anything until I draw a picture or make a simulation of it. All right. So I'm going to do that really quick. So to do that, I need to erase something. I'm going to erase all this mess. Remember, you got more neatly written examples in your book. So according to this, we figured out it was 29.3 degrees, right? So let's try and draw this and see what it looks like. One of these has got a large negative. Doesn't look like anything's going upwards, so I'll do this. And I'm going to try and draw it approximately to scale to get a feel for it. All right, so B is over 2, 1, 2, down 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that perfect? No, but it's kind of close. We see it's got a small x and a huge negative y. Now I'm going to do the other one. 1, 2, 3, 1, 2, 3, 4. Looks like about 30 degrees to me. Looks like my math is good. That's all the picture's good for, right? To kind of give you a feel if you screwed up your math or not. Did you remember the degrees button in your calculator, or did you make some other stupid mistake with the minus sign? That's what drawing pictures helps you with. So you could try and get through life without it. But I got to tell you, I've been doing this a long time. I make a lot of mistakes. You're going to make a lot of mistakes too. You just can't be perfect day in and day out doing calculations. You've got to have ways to check your work. That's what all these little pictures and stupid stuff are good for. Okay. All right. And I don't know, I kind of enjoy it too. It's just fun to visualize things. Yeah. It doesn't have to be perfect. All right. All right. So if you wanted it to be perfect, who was that? Jacob? How could I make it perfect?
I mean, you can use you can use a computer, or you can just accurately count down and make sure you're using graph paper or something.
And the fastest way is to go into here and uncomment some of this crap. Type in the arrows. What do we have? 3, -4, 0. Wait, 3, -4, 0. And so let's get it perfect. 2, -15. And I think drawing it by hand, kind of close, is a good thing to practice. And that was kind of like my picture. It's not perfect, but you can kind of see it there. And let's call that good for that. All right. And so this lecture I did a little bit differently than the last lecture. So in the last lecture, I didn't do any of the computer simulation stuff because, like I said, I wrote that in office hours because a student said that would help him. So if you want I did do a very brief introduction to cross products in the other lecture. So if you're wanting to get a little bit ahead on cross products, you could go back and watch that other video lecture. Also, you could just really forget about cross products until next Wednesday, and I'll just handle that then. And so, but I do think the more work you get done before next Wednesday's class, the easier it is for me to help you, because I don't know what questions you have. You don't know yet. You gotta struggle with the math and screw up and find out what you don't understand. And that's what I'm actually useful at helping you. I'll be like, oh, I think you need this, this, and this, right? That's going to be better than me just babbling to you over Zoom. So if you could do more work by Wednesday and get as many problems done from that email, and let's see if I have that somewhere. Inbox. Do I have my sent emails? And I know I just said this to you, but sometimes it's nice to just talk. Oh my gosh, it's making me log in. Sorry. Oh my gosh, no, it's not. I don't understand. Oh, Hancock. Where is it? Where is it? All right, and let me share screen too. Sorry. You're welcome to take off, but I'll show you this email if you want to stick around for 1 minute. Zoom stuff drives me crazy. All right, so those of you, this is the email I just sent you, so you've got this. The link to the code is right there. Now, you're not going to be able to change the arrows, but what you can do is read these instructions, basically set up your own GlowScript account, and then you can cut and paste my code into your codes, and you can deal with it there. If you don't know how to start up with GlowScript, all the instructions are inside there, okay? Now, these are the problems that you could do. I would try and get these done before the weekend, everything up to 3.9. If you don't have that done by this week, you're just going to be miserable next week. And then if you can, these are the ones that don't have cross products. So try and do those. And then there's all your holidays and quiz crap. All right. So, all right. Did I stop the live stream yet? No, I didn't. So, all right. I better stop that.